Hello everybody, myself Jyoti and this is fourth lecture on physics of semiconductors. Today we will discuss about impurity semiconductors or extrinsic semiconductors. There was a lecture at the University of Pennsylvania in 1948 when Horowitz he described the study of semiconductors as an investigation of physics of drift. So today what we are going to discuss is about physics of drift. So the reason for this statement lay in a fact that when we talk about the electrical properties of solids, they are extremely sensitive to the presence and nature of even the tiniest amount of impurity in the lattice. Like आपके पास कोई भी material है and if you have a solid and if you dope any kind of impurity in it, even if there is the tiniest impurity in it, electrical properties of that particular solid it will change drastically. So if you have a solid, then electrical properties are so sensitive that even if there is an impurity 1 part in 10 raised to 11, still it is going to cause a problem. Electrical properties will do change. Now when we have methods to detect impurity in a solid, the chemical methods which were there earlier, they were able to detect impurities only 1 part in 10 raised to 7 or 10 raised to 8 at best. So that is how physicists they struggled for decades to purify semiconducting materials to a very high degree. Now when we talk about pure semiconductors, like we have seen that physicists they were focusing more and more on making semiconductors pure in nature because the electrical conductivity it is sensitive to purity. But when we talk about pure semiconductors, they are of theoretical interest only. Why? By 1958, as physicists they were trying to make the semiconductors pure. By 1958 they were able to do that. They were able to make many solids like silicon, germanium. They were able to refine these materials to such an extent that unwanted impurities, if they are present, they will not cause any kind of a problem. The ability to grow large pure single crystals was one of the main aids in advancement of semiconductor technology. But when we talk about pure semiconductors, they are of theoretical interest only, because when we talk about pure semiconductor or intrinsic semiconductor, we have charge carriers like electrons as well as holes at normal temperature, and uh, at the normal at normal temperature the charge carrier concentration it is very low, and hence for an appreciable current density through that semiconductor we will have to apply a very large electric field. So if there is a need to apply very large electric field, naturally we are not interested in that kind of material. So when we talk about this electrical conductivity of semiconductor, it depends upon two factors. One is its purity, and second, it also depends upon imperfections in the lattice, or what we call as a defects in the lattice. So if you want to increase the conductivity of semiconducting crystal, one of the way is to add a controlled amount of certain impurities. So for instance, conductivity of silicon, it can be increased 1,000 times if we add boron, which is a trivalent impurity. How much boron we have to add? 10 parts per million, means 10 parts per 10 raised to 6. Very small impurity we have to add. And the conduction that occurs because of the addition of these impurity atoms, that is called as impurity conduction. And this impurity conduction it is very important in the operation of semiconductor device. And the impurities, like we have discussed in the earlier lecture, like we add trivalent impurities, we add pentavalent impurities, and these impurities which we add, they are called as dopants. So We have already discussed trivalent, pentavalent impurity, but again we will discuss it. So look at this figure. So suppose we have this silicon structure, where silicon in the outermost shell, it has four valence electrons which are shared with by the four neighboring silicon atoms. Now at room temperature, at a very low temperature, suppose I haven't added any impurity. Imagine that instead of P in the middle, I have silicon atom only. Then all these four electrons are shared by four nearby silicon atoms, and in that case there will not be any kind of conduction at low temperature, because they are the electrons are shared by covalent bond with the neighboring atoms. Now as the temperature is increased, like at room temperature, what happens at room temperature? Like suppose I take the temperature as 300 Kelvin. Some of these covalent bonds are broken, electrons are set free, and then the conduction will happen. But suppose I want conduction at a low temperature. So here what I can do is I can either add pentavalent impurity or I can add trivalent impurity. Now take the example, what happens when we add pentavalent impurity. Phosphorus, it is an element which has 5 valence electron in its outermost shell. So it is a pentavalent in nature. So this phosphorus atom, and one more thing is, when you compare size of phosphorus and size of silicon, it is almost same. So whatever lattice site which is available for silicon, that lattice site can be taken by this phosphorus atom, because both of them, they share the same size. So now this phosphorus, it has replaced one of the silicon atom. Phosphorus has 5 electrons in its outermost shell. 4 electrons will be shared by the neighboring 4 silicon atoms, and 1 electron is free. Here you can see that 1 electron is free. This free electron, it is available as a charge carrier for the conduction of current. Now when we take the example of solid, we have a valence band, we have a conduction band, and here you can see there is one level which is called as donor level. So we have a donor level which is near to the conduction band, ED. You can see ED, which is close below the conduction band. Now when you have this extra electron, like in phosphorus, 4 electrons are shared with neighboring silicon atoms, 1 electron is extra. Those electrons, they are available for conduction below room temperature. Even if the temperature is less than 300 Kelvin, they will be there available. At 0 Kelvin, what will happen? They will occupy an energy level which will be below the conduction band, and that is ED. So these are donor levels. So at 0 Kelvin, these donor levels are occupied. Now, what happens when the temperature is greater than 0 Kelvin? When the temperature is greater than 0 Kelvin, as this gap between EC and ED, it is small. You can see there is a very small gap. So this gap, when the temperature is greater than 0 Kelvin, naturally the electrons will gain thermal energy, and because of that, they will go from donor level to conduction band, and that is how the current will increase. Now, when the temperature is 300 Kelvin, that means room temperature, that time we know that at room temperature in semiconductors, some of the covalent bonds are broken, and that is how conduction takes place. So the energy which is available here, it is equal to Eg. EV minus EC, that is Eg. So that much energy is available at room temperature, and electrons from valence band can also go to the conduction band. So that is how when the temperature is 300 Kelvin, we are having current because of the donor levels, electrons from the donor levels which are going to conduction band, as well as the covalent bonds are broken and electrons are going to the from valence band to the conduction band. So the fifth electron which occupies a state, that donor level, it is just below the conduction band, and that energy gap, it is of the order of 0.045 electron volt. So since the ionization energy for phosphorus is much smaller than the energy E, required to break one of the valence bonds, the phosphorus atoms will donate this fifth electron to the conduction band even at much lower temperature than the valence band will. And an impurity of this kind, where it is donating electron at a temperature which is less than the room temperature, that is called as a donor, and since it donates conduction electrons without producing holes in the valence band. So the donor level represents the ground state of the fifth electron of the impurity atom. So what is N-type semiconductor? If pentavalent impurity exists in an otherwise intrinsic semiconductor, electrons are added to the conduction band, outnumbering the holes in the valence band, and the electron then becomes the majority carrier. So N-type semiconductor, basically you can say it is a semiconductor where electrons are the majority carriers and holes are the minority carriers, and the electrons are majority carriers and thermally generated holes are the minority carriers. In N-type semiconductor, if N and P, it represent the number of electrons and holes, like electron and hole concentration, we can show that NP, it is equals to NiPi. What is NiPi? It is the concentration of electrons and concentration of holes in the intrinsic material, in the pure material, and that this product remains constant. So if this product has to remain constant, what will happen? That P, it is greater than Pi, but N is greater than Ni, so that the product NP, it will be equals to NiPi. Now what happens when we add the trivalent impurity? So let us look at this figure. So in here, instead of phosphorus, now what we have added is boron. Boron, it is a trivalent atom, like boron, aluminium, you can add that. So in case of boron, there are 3 electrons in the outermost shell. So these 3 electrons are shared with the 3 neighboring silicon atom, but with 4th atom, it cannot share anything because it has only 3 electrons. So there will be a vacancy. That is what is called as a hole. Now, when the temperature is 0 Kelvin, at that time, these holes are available at the acceptor level, and this acceptor level EA, it is close to the valence band. So what will happen is, when you will increase the temperature, when the temperature is increased, it is greater than 0 Kelvin, then electrons from the valence band, they go to the acceptor level. So acceptors have accepted electrons from the valence band. Here T is greater than 0 Kelvin but less than 300 Kelvin. When the temperature is 300 Kelvin, some of the covalent bonds break and you again have a charge carriers which are there. So at T equals to 300 Kelvin, what happens? Electrons from the acceptor levels, they jump to the conduction band, and again electrons from the valence band, they go to the acceptor level as well. So this is what is happening. So what is acceptor impurity? The 3 valence electrons enter into covalent bonding, but a region of stress exists where the 4th bond ought to be, and any stray electron in the vicinity can be trapped by the impurity center, which then becomes negatively charged. The region from which electron came is positively charged. In effect, the trivalent impurity has injected a hole into the crystal. Such an impurity, it is called as acceptor impurity because it is accepting electron, right? So silicon or germanium doped in this way has many holes as charge carriers, and therefore it is termed as p-type semiconductor. Again, here the product Pn is equals to Pi Ni, that will remain constant. So here in this case, P will be greater than Pi but N will be less than Ni, so that the product Np, it is equals to Nipi, should remain constant. So what is the summary? What we conclude here, in N-type semiconductor, electrons are majority charge carriers. Some holes exist owing to the formation of electron hole pairs at room temperature, and these are minority carriers. Alternatively, in p-type semiconductor, we have holes as the majority charge carriers and electrons and minority carriers, and the number of charge carriers which are available, they determine the resistivity. So if you take the example of germanium or silicon crystals used in devices, they have resistivity of the order of 0.00152 ohm meter to 0.12 ohm meter after the impurities have been added. So that's all about this extrinsic semiconductor and role of impurity when we add, what happens exactly when we add trivalent impurity and pentavalent impurity in terms of conduction band, valence band, acceptor level, donor level, and all that. So thank you so much.